Since late December, the Hunga Tonga Hunga Ha'apai volcano had been showing signs of increased activity. A series of moderate eruptions had already been noted by local scientists, but nothing had prepared them for what would happen on January 14th. On that day, the volcano erupted again, and this time, it was different. A massive towering column of ash was launched into the sky, reaching 20 kilometers into the atmosphere. From the ground, it looked like a huge, ominous plume stretching into the heavens. A terrifying and majestic sight for those who witnessed it. But that was only half the story. What people saw on land, despite its intensity, paled in comparison to what would soon be observed from orbit. The following day, something extraordinary happened. Satellite imagery revealed the true scale of the eruption, and it was breathtaking. Music fades in. Two powerful geostationary satellites, GOES West and Himawari 8, captured the massive explosion from space. What they recorded shocked scientists across the globe. A massive circular shockwave radiated from the volcano, resembling the detonation of a nuclear bomb. The eruption formed a near-perfect ring of ash and vapor that spread rapidly across the Pacific. For the first time in history, we were witnessing a volcanic eruption from a space-based perspective, in near real time. And it was more immense than anyone had imagined. This wasn't just a typical volcanic eruption. The Hunga Tonga blast was estimated to be one of the most powerful eruptions ever recorded using modern instruments. The force of the explosion was so extreme that it sent atmospheric pressure waves rippling around the entire planet, multiple times. Some instruments even picked up the pressure fluctuations in Europe and Africa, thousands of kilometers away from the blast site. Scientists were stunned by the intensity. The eruption not only created a massive ash cloud, but also generated a powerful sonic boom, so strong, in fact, that it was heard as far away as Alaska, over 9,000 kilometers from Tonga. That's equivalent to hearing a thunderclap on the other side of the Earth. The satellite images continued to circulate around the world. They showed the colossal plume rising vertically from the sea and spreading outward in all directions, a stark white mushroom cloud against the blue curve of the planet. The eruption was not just large, it was beautifully symmetrical, shockingly clean in shape, and eerily reminiscent of man-made explosions. But this was nature at work, and nature was showing us just how powerful it could be. What made the eruption even more astonishing was how it managed to reach the mesosphere, the third layer of Earth's atmosphere, a region typically untouched by volcanoes. According to NASA, the plume reached over 58 kilometers, 36 miles in altitude, making it the highest recorded volcanic plume in history. That's higher than most commercial aircraft fly and well into the upper reaches of the stratosphere. For days, the skies over the Pacific were filled with ash and water vapor. The plume injected an estimated 50 million tons of water into the atmosphere, something that could have implications on the Earth's climate for years to come. Unlike other large volcanic eruptions that typically cool the planet by blocking sunlight with sulfur dioxide, the Hunga Tonga blast may do the opposite. The enormous amount of water vapor it released could potentially warm the stratosphere, a phenomenon not commonly observed after eruptions. From the small islands of Tonga, people were still trying to grasp the magnitude of the event. The eruption triggered tsunami waves that struck coastlines across the Pacific Ocean, from Japan to South America, and even reached parts of the United States. In Tonga itself, the damage was catastrophic. Ash covered entire villages, contaminated freshwater supplies, and disrupted communications for days. But perhaps the most iconic aspect of this eruption will forever be the view from space, an apocalyptic sight unfolding in slow motion, watched by millions across the planet. It was a stark reminder of Earth's raw power, hidden beneath the ocean's surface, and how quickly that power can be unleashed. At infinity beyond, We dive deeper into stories like this, where science meets spectacle, and Earth shows us its might in ways we never imagined. Stay with us. In the next segment, we'll explore what caused such an intense underwater explosion and how scientists are still uncovering the secrets behind the Hunga Tonga Hunga Ha'apai event. As we witnessed in Segment 1, the eruption of the Hunga Tonga Hunga Ha'apai volcano was not only spectacular, it was mysterious in its sheer violence. Scientists around the world began to ask the same question. Why was this underwater eruption so explosively powerful? To find the answer, we need to dive, quite literally, beneath the ocean's surface, into the heart of what makes underwater volcanoes so dangerous. Unlike land-based volcanoes, submarine volcanoes are often hidden beneath hundreds or even thousands of meters of water. When they erupt, the interaction between hot magma and cold seawater creates a unique and volatile dynamic. It's not just about heat, it's about pressure, chemistry, and physics all colliding at once. When magma, molten rock from the Earth's mantle, rises to the surface and meets seawater, it causes what scientists call phreatomagmatic explosions. These occur when intense heat causes the water to flash into steam instantly. That sudden phase change from liquid to vapor creates a violent burst of energy, far greater than the lava itself might produce. But in the case of Hunga Tonga, something more happened. The Hunga Tonga Hunga Ha'apai volcano sits along the Tonga-Kermadec subduction zone, one of the most active tectonic areas in the world. Beneath the ocean floor, a massive supply of magma had been building up for years, slowly pushing toward the surface. Unlike typical eruptions, this one occurred in a shallow marine environment, just about 150 to 200 meters below sea level. The sweet spot where pressure is low enough for an explosion to breach the surface, yet deep enough to trap pressure long enough to make it catastrophic. When the eruption finally happened, the result was an enormous blast of steam, gas, and ash, ejected vertically with such force that it reached the mesosphere, something never before observed. But what really amplified the eruption was the geometry of the volcano itself. Recent bathymetric surveys showed that Hunga Tonga had a caldera, a collapsed volcanic crater, that was partially submerged. This allowed seawater to rush in and mix with the hot materials as pressure increased, essentially creating a giant pressure cooker under the ocean. Once the system failed, the trapped gas expanded violently, and the explosion was released with a power equivalent to several hundred Hiroshima bombs. This interaction between magma, seawater, and confined gas created what some scientists described as a perfect storm of volcanism. The energy release was so intense that it generated shock waves in the atmosphere that traveled around the planet multiple times. Meteorological stations in Europe, Australia, and even Antarctica picked up the wave patterns hours after the eruption. Another surprising factor was the amount of water vapor injected into the upper atmosphere. Unlike sulfur dioxide, which reflects sunlight and cools the planet, water vapor acts as a greenhouse gas. The Hunga Tonga eruption sent nearly 10% of the total stratospheric water content into the atmosphere in a single event. This has potentially long-lasting implications for global climate dynamics, especially stratospheric heating. The explosion also sent a tsunami across the Pacific. Waves were detected as far away as Peru and California. But the real devastation was felt in Tonga, where the force of the wave, coupled with the ashfall, disrupted nearly all communication, damaged water supplies, and left thousands in crisis. Perhaps the most fascinating aspect was how quickly all this occurred. Within just a few minutes, satellites were capturing images of a massive cloud expanding with perfect symmetry. Scientists later analyzed those images frame by frame to estimate the velocity of the ejected material, some traveling over 300 meters per second, or close to the speed of sound. As we learn more, it becomes clear that this eruption wasn't just rare. It was unique in modern history. Not since the eruption of Krakatoa in 1883 had the world seen such a large-scale explosion from a volcanic source. And unlike Krakatoa, which relied on reports from ships and observers, the Hunga Tonga eruption was witnessed by the entire planet, through the eyes of satellites and sensors in real time. At Infinity Beyond, we continue to explore the unseen forces shaping our planet. Stay with us, because in the next segment, we'll reveal how scientists are using this eruption to rethink how we monitor volcanic threats under the ocean, and why the next eruption might not give us any warning at all. After the world witnessed the eruption of Hunga Tonga from space, a new question began to echo throughout the scientific community. Can we detect eruptions like this before they happen? And more importantly, can we stop them from becoming disasters? In this episode of Infinity Beyond, we explore the technology that scientists are using right now and the innovations coming next to monitor volcanic activity around the globe, especially under the sea. First, it's important to understand that satellite monitoring has revolutionized how we study volcanoes. Using a network of Earth-observing satellites, scientists can now detect even the smallest changes in a volcano's surface. These satellites use a technology called INSAR, Interferometric Synthetic Aperture Radar, which sends radar signals down to Earth and measures the ground's movement with centimeter-level precision. Before Hunga Tonga erupted, INSAR had already detected subtle uplift of the seafloor in the area, indicating that magma was rising beneath the surface. But unfortunately, the region lacked real-time systems to trigger a public warning. Tonga's isolation and limited infrastructure meant that the volcano wasn't being watched continuously. By the time the eruption occurred, it was too late for any alert to reach the coastal communities in time. That's where new global monitoring systems come into play. Agencies like NASA, NOAA, and the European Space Agency are now coordinating to ensure that satellites pass over high-risk volcanic regions more frequently. Some satellites are equipped with infrared sensors, capable of detecting changes in temperature or heat anomalies, even if the volcano is underwater. But satellites aren't the only tools. Scientists are also deploying ocean-bottom seismometers, specialized sensors that sit on the seabed and listen for tremors. These instruments are connected through a network known as seafloor observatory systems, which can detect early signs of magma movement. If something changes, like a sudden tremor or shift in pressure, it can send data back to researchers in real time. Another game changer, artificial intelligence. AI is now being used to scan satellite images, seismic patterns, and gas emission data to identify early signs of eruption. By training machine learning models on thousands of volcanic events, scientists can create predictive models that issue warnings, sometimes days or even weeks before a major event occurs. The Hunga Tonga eruption exposed a critical weakness in our current monitoring network. Underwater volcanoes remain the least understood and least observed. Unlike land-based volcanoes, which are often ringed with sensors, many submarine volcanoes have no instruments near them at all. And yet, 70% of Earth's volcanic activity occurs underwater. One promising solution is the deployment of autonomous underwater vehicles, AUVs, robotic submersibles that can map the seafloor, detect temperature anomalies, and measure gas emissions. These robots can operate for months at a time, swimming over vast areas to collect data that would otherwise be impossible to gather. Meanwhile, new satellite missions like Sentinel-1, Landsat-9, and TerraSAR-X are being launched with the goal of improving volcanic surveillance. These satellites can deliver updates as often as every 6 hours, providing near real-time insights into volcanic changes. But even with all these tools, predicting an eruption is still more art than science. Volcanic systems are incredibly complex. Not all uplift leads to eruption. Not all earthquakes signal magma. And not all eruptions are catastrophic. What made Hunga Tonga unique was not just its scale, but the lack of precursors. There were few tremors. There was no significant sulfur emission spike. The system went from quiet to apocalyptic in less than 24 hours. That has led many volcanologists to propose a new model for submarine eruptions, one that includes hidden magma chambers and hydrothermal instability as triggering factors. The good news is that this eruption has sparked a global effort to improve early warning systems. Tonga is now receiving support from international partners to rebuild and modernize its volcano monitoring stations. Satellite access is being expanded, and the event has prompted the Pacific Tsunami Warning Center to re-evaluate how submarine explosions are detected and analyzed. The world is waking up to the fact that our greatest threats may lie beneath the waves, hidden but not invisible. At Infinity Beyond, we believe that understanding these dangers is the first step in protecting lives. And as we continue to explore the frontier between Earth and space, we invite you to join us, because the next eruption could come from anywhere, at any time. In Segment 4, we'll explore how this eruption affected Earth's atmosphere, and whether the massive plume of water vapor could change global weather patterns in the years to come. The eruption of Hunga Tonga Hunga Ha'apai was not just a visual spectacle. It was an atmospheric event of global proportions. Scientists soon realized they weren't just dealing with a geological explosion, but with something that reached into the skies and potentially into the planet's climate systems. So the question is, did the Hunga Tonga eruption actually change Earth's climate? At first glance, it seems like a strange question. Most large volcanic eruptions, like Mount Pinatubo in 1991, are known to cause global cooling. That's because they eject massive amounts of sulfur dioxide, SO2, into the stratosphere. These sulfur particles reflect sunlight, creating a temporary sunshade that cools the Earth for months or even years. But Hunga Tonga was different. NASA's satellites quickly revealed that the Tonga eruption did not release much sulfur dioxide, but it did inject an extraordinary amount of water vapor into the stratosphere. Estimates suggest that more than 146 teragrams, or 146 million tons of water, were blasted into the upper atmosphere. To put that in perspective, that's enough water to fill 58,000 Olympic-sized swimming pools, all suspended in the air above our planet. This sudden, massive surge of water vapor has never been observed before. In fact, it was the single largest increase in stratospheric water content ever recorded. And unlike sulfur dioxide, water vapor is a greenhouse gas. It traps heat instead of reflecting it. Scientists at NASA's Jet Propulsion Laboratory warned that this increase could lead to a temporary warming of the stratosphere. This might sound subtle, but it has big consequences. A warmer stratosphere can influence jet stream behavior, ozone chemistry, and even the development of extreme weather patterns across continents. So how did the water get there? The eruption's explosive force sent materials vertically at supersonic speeds, shooting well into the mesosphere, over 58 kilometers above the Earth's surface. As the steam rose, it bypassed the troposphere, where weather occurs, and entered the stratosphere directly, where water vapor can remain trapped for years. Typically, this region of the atmosphere is cold and dry, so when a sudden surge of moisture is introduced, it doesn't just disappear. It interacts with existing chemical systems, like ozone molecules, potentially altering their balance. Some scientists now fear that this excess water could lead to stratospheric ozone depletion, weakening Earth's natural UV shield. But the effects don't stop there. Climate models are now being adjusted to include this moisture anomaly. While it's unlikely that the Hunga Tonga eruption will drastically warm the entire planet, It could slightly shift global temperatures upward for a few years, a rare phenomenon for a volcanic event. That's not all. The eruption also disrupted weather patterns across the Pacific for weeks. Shifts in pressure and atmospheric dynamics created unusual storm systems, increased rainfall in some regions, and prolonged droughts in others. Meteorologists observed atmospheric waves that rippled across the globe, altering wind currents in the southern hemisphere. It's the first time in modern history that a volcanic event may have warmed the Earth's climate instead of cooling it, and that opens up an entirely new chapter in climate science. Could future eruptions like this accelerate warming trends already in motion due to human activity? Could an underwater volcano become a wild card in our climate system, unpredictable, unstoppable, and invisible until it's too late? At Infinity Beyond, we explore not just the what of science, but the what if. And in this case, what if a single eruption altered our atmosphere enough to change the balance of weather, energy, and ozone around the world? It's a sobering thought, but also a reminder that we must observe our planet more closely than ever. Because the forces that shape our future might come not from industry or cities, but from deep beneath the ocean floor. In the next segment, we'll explore how this eruption was captured by civilian cameras, sensors, and even social media, and how the digital age gave us the first truly global, crowdsourced volcanic disaster archive. Stay curious, stay informed, stay with Infinity Beyond. The eruption of Hunga Tonga Hunga Ha'apai wasn't just a geological event, it was a digital phenomenon. For the first time in history, a volcanic disaster was witnessed, shared, and archived in real time by millions around the globe, not just by professionals or scientists, but by everyday people with smartphones. This segment of Infinity Beyond explores how social media transformed our understanding of the eruption, and how platforms like TikTok, Twitter, and YouTube became unexpected tools for geoscience. Within minutes of the explosion, videos began surfacing online. In Tonga, residents filmed walls of water crashing into villages, clouds of ash blanketing the sky, and even the sound shockwave, which echoed with a deep, otherworldly rumble. Although much of Tonga lost communication due to undersea cable damage, a handful of clips were uploaded in the immediate hours before the blackout. Thousands of kilometers away, people in New Zealand, Fiji, and even Alaska uploaded videos of sonic booms, air pressure shifts, and tide surges. One viral TikTok from Samoa showed the sky lighting up with a distant flash, just seconds before a loud blast, evidence of how the eruption's energy traveled through the air. Then came the satellite overlays. Data from Goes West and Himawari 8 was synced with civilian videos, showing the mushroom cloud as it expanded, and how it correlated with wave arrivals in various regions. Scientists on Twitter began stitching together footage with timestamps to build a timeline of the eruption and its worldwide impact. Astonishingly, some of the most valuable footage came from doorbell cameras and home security systems. In California, smart devices picked up low-frequency rumbling and pressure changes, essentially serving as accidental seismographs. Several clips were used by researchers to triangulate the arrival time of the atmospheric wave in North America. But perhaps the most unexpected outcome was how social media became a real-time archive. On YouTube, long-form live streams showed people reacting to tsunami alerts. On Reddit, meteorology and geology communities pieced together wind data, eruption physics, and satellite readings. And on Twitter, volcanologists used hashtags to direct the public toward verified information and debunk myths as they emerged. This wasn't just public participation. It was citizen science on a global scale. The Tonga eruption marks the first time that crowdsourced video and audio were used to supplement official scientific data sets for a volcanic event. In fact, several academic papers have already cited TikTok and YouTube footage as primary data sources, helping to model the eruption's acoustic profile and global wave propagation. But there were challenges. Misinformation spread quickly. Some users uploaded footage of unrelated eruptions, passing them off as Hunga Tonga. Others exaggerated tsunami heights or shared edited audio to create more drama. Platforms had to respond quickly, and scientists scrambled to separate fact from fiction. Still, the overall impact was overwhelmingly positive. Never before had the public been so deeply involved in documenting a planetary-scale disaster. And for scientists, it was a rare opportunity to study human reactions to a natural catastrophe in real time, from fear and awe to curiosity and collaboration. This fusion of technology, human behavior, and geoscience has now become a model for future disaster response. Several space and climate agencies are developing platforms to integrate social media inputs into live monitoring dashboards, combining satellite data with on-the-ground reports. Imagine a world where your smartphone could become part of the global early warning system, where a video you upload might help track a tsunami wave or confirm the arrival of a shock wave. We're not far from that world now. As we look ahead, the Hunga Tonga eruption serves as a stark reminder that we are all observers of Earth's story, not just through science, but through the lens in our pockets. In Segment 6, we'll explore the long-term recovery of Tonga and how nations respond to large-scale natural disasters in the age of climate instability. Stay tuned with Infinity Beyond, because the way we understand disasters is evolving, one upload at a time. When the sky cleared and the satellite imagery faded from headlines, a sobering reality settled in. Tonga was devastated. Entire islands were blanketed in ash. Homes were swept away by tsunamis. Freshwater supplies were contaminated, and communications were lost. But for the people of Tonga, this was just the beginning, the start of what would be a long, challenging road to recovery. In this episode of Infinity Beyond, we shift our focus from the eruption itself to its aftermath, examining what it means to rebuild a nation after one of the most powerful volcanic events in modern history. The initial damage was staggering. According to the Tongan government, 84% of the population was directly affected. On the hardest-hit islands, like Mango and Atata, nearly every home was destroyed. Entire villages were reduced to rubble. Crops and livestock, the lifeline for many communities, were wiped out under thick volcanic ash. And the most immediate challenge? Clean water. Volcanic ash had coated nearly every surface, including rainwater collection systems, the primary source of drinking water on many islands. With supplies dwindling, the risk of disease loomed large. Aid organizations like the Red Cross, UNICEF, and Oxfam mobilized quickly to send water purification kits, sanitation gear, and emergency food supplies. But delivering aid was not easy. The eruption severed Tonga's only undersea internet cable, cutting off communication with the outside world for days. Satellite phones became the country's only link to international partners. Airports were closed due to ash buildup, and debris blocked sea routes. Tonga, one of the most remote countries on Earth, had become even more isolated at its moment of greatest need. Despite these hurdles, the world responded. Australia, New Zealand, Japan, the United States, and the United Nations led major relief efforts, sending military transport planes, naval vessels, and humanitarian teams. One of the key concerns was maintaining COVID-19 protocols during aid deliveries, a difficult task in a country that had largely avoided the virus until then. Tonga's diaspora, particularly in Australia and New Zealand, also played a vital role. Crowdfunding campaigns, donation drives, and cultural fundraisers quickly raised money and awareness. The eruption had not only shaken the islands, it had unified Tongan communities around the globe. But beyond the emergency response lies a much bigger question. How do you rebuild in an era of climate uncertainty and geological risk? Tonga's government, along with international climate organizations, began developing a long-term recovery plan. This included reinforcing coastal infrastructure to better withstand future tsunamis, relocating communities from high-risk zones, building ash-resistant housing with local and sustainable materials, strengthening early warning systems with satellite and seismic data integration, replanting agriculture using volcanic-enriched but ash-covered soil. However, these are not quick fixes. Rebuilding is a process measured in years, not weeks. And for many Tongan families, the trauma lingers. Schools, churches, and places of worship, centers of community life, were also damaged or destroyed. In interviews conducted by aid workers and local journalists, many Tongan residents expressed both gratitude and grief. Gratitude for having survived, and for the outpouring of support, but grief for what was lost. Homes, loved ones, and the fragile sense of security that existed before the eruption. There is also growing concern about future resilience. As climate change intensifies storms, sea level rise, and heat waves, many small island nations like Tonga face compounding threats. A volcanic eruption in isolation is devastating. Combined with other environmental pressures, it becomes catastrophic. That's why Tonga is now working closely with regional partners to become a model of climate-adaptive recovery, integrating modern technology with traditional knowledge to create communities that can survive and even thrive in the face of disaster. One initiative involves training local youth in GIS mapping, emergency logistics, and renewable energy deployment, turning recovery into an opportunity for education and empowerment. Another innovation is the development of community-based alert systems, low-tech but highly effective solutions like radio beacons and hand-cranked sirens that can be deployed even in remote villages. It's not just about rebuilding what was lost. It's about building smarter, safer, and stronger. As we close this segment, the story of Tonga reminds us of something profound. Nature can destroy in moments, but recovery takes unity, science, and human spirit. In Segment 7, we'll explore how volcanic eruptions have shaped human civilization throughout history, from ancient myths to modern resilience, and what we can learn from our ancestors as we prepare for the next great blast. Stay with Infinity Beyond, where Earth's past, present, and future collide in stories that matter. Volcanoes aren't just natural disasters. They are forces of transformation that have shaped the story of humanity in profound and often forgotten ways. In this segment of Infinity Beyond, we journey through time to explore how eruptions have rewritten history, from ancient cities buried under ash to climate events that changed the fate of civilizations. Let's begin with the most iconic volcanic catastrophe in human memory, Pompeii. In 79 AD, Mount Vesuvius erupted violently, burying the Roman cities of Pompeii and Herculaneum under meters of ash and pumice. The eruption killed thousands, preserving their last moments in haunting detail. For centuries, the cities remained entombed, forgotten, until excavations revealed an almost perfectly preserved snapshot of Roman life. But beyond the tragedy, Pompeii taught us something deeper. Volcanoes are historical markers, freezing time and reshaping how we understand ancient societies. Now fast forward over 1,000 years to another massive eruption, one that changed the climate of the entire planet. In 1815, Mount Tambora in Indonesia unleashed the most powerful eruption in recorded history. The explosion was so intense that it blasted billions of tons of ash into the stratosphere, blocking sunlight and cooling the earth. The year that followed became known as the Year Without a Summer. Across Europe, North America, and Asia, crops failed. Famines spread. In Switzerland, a young Mary Shelley, trapped indoors by the bitter weather, wrote Frankenstein, inspired by the darkened skies. In India and China, monsoons were disrupted, and widespread starvation followed. This was not just a natural disaster. It was a global climate shock that affected millions, without anyone understanding the true cause. Centuries earlier, another catastrophic eruption, possibly of the Thera volcano in the Aegean Sea, may have played a role in the collapse of the Minoan civilization. Some historians believe the eruption caused massive tsunamis that devastated coastal cities, or triggered economic turmoil that weakened the once great maritime power. Even in mythology, volcanoes left their mark. The ancient Greeks believed Mount Etna was the forge of Hephaestus. Polynesians told of fire gods and island birth from the sea. These weren't just stories, they were cultural memory, encoded warnings passed down through generations. Fast forward again, this time to the 20th century. In 1980, Mount St. Helens erupted in Washington state, killing 57 people and reshaping an entire mountain. In 1991, Mount Pinatubo in the Philippines erupted just days after scientists issued an evacuation warning, one of the most successful disaster prevention operations in volcanic history. That eruption, like Tambora, injected millions of tons of sulfur dioxide into the stratosphere, lowering global temperatures and providing crucial data on atmospheric dynamics, data that is still being used in climate models today. So what connects all these events, from ancient Rome to modern Tonga? Volcanoes remind us that we are never fully in control. Despite all our science, technology, and infrastructure, Earth can still surprise us. And sometimes, it rewrites our story in ways we never expected. But there's another thread: resilience. History shows that civilizations have always recovered, adapted, and evolved in response to volcanic events. In the aftermath of Pompeii, the Roman Empire didn't fall. It grew. After Tambora, science advanced, art flourished, and new systems of weather observation emerged. After Pinatubo, volcanology transformed, and lives were saved as a result. And after Tonga, we are witnessing a similar pivot, one that blends technology, community, and historical awareness. What if future eruptions were seen not only as threats, but as catalysts for scientific innovation, international cooperation, and cultural evolution? At Infinity Beyond, we believe that understanding the deep past of volcanic history can help us prepare for the deep future. Because the ash layers of Earth are not just geological strata, they are chapters in the human story. In Segment 8, we'll explore how volcanologists are preparing for the next supervolcano, and whether Earth is overdue for an eruption that could dwarf even Tonga and Tambora. Stay curious, stay alert, stay with Infinity Beyond. Throughout this series, we've explored how volcanic eruptions can reshape the land, alter the atmosphere, and change human history. But what happens when an eruption doesn't just impact a region, but the entire planet? Welcome to the terrifying world of supervolcanoes. In this segment of Infinity Beyond, we investigate what defines a supervolcano, why Yellowstone has captured global attention, and whether humanity is truly prepared for an eruption that could darken skies and disrupt life for years. First, let's define the term. A supervolcano is not just a big volcano. It's a volcanic system capable of ejecting more than 1,000 cubic kilometers of material in a single eruption. That's enough to bury entire continents under ash and alter the global climate for decades. There are only a handful of supervolcanoes on Earth. These include Yellowstone Caldera, USA, Lake Toba, Indonesia, Campi Flegrei, Italy, Taupo Volcanic Zone, New Zealand. Each of these sites is massive in scale, often covering hundreds of square kilometers. And all of them are being closely monitored by scientists. Among them, Yellowstone is perhaps the most infamous. Located in Wyoming, Yellowstone National Park sits atop a massive volcanic system that has erupted 3 times in the last 2.1 million years. The most recent eruption occurred around 640,000 years ago, forming the Yellowstone caldera, a depression so large most visitors don't even realize they're standing inside a volcano. Since then, the system has remained active, with earthquakes, geysers, and ground uplift as constant reminders of the power beneath. But here's the question that keeps researchers awake at night. Are we overdue for another super eruption? Statistically, it's complicated. While some have claimed that Yellowstone erupts every 600,000 to 700,000 years, scientists caution against using averages to predict rare geological events. Nature doesn't follow a schedule. That said, the potential consequences of an eruption are staggering. If Yellowstone were to erupt at full force, it could eject thousands of cubic kilometers of ash into the sky, create a volcanic winter, blocking sunlight and reducing global temperatures, collapse agriculture in major food-producing regions, contaminate water sources and cause mass displacement, severely disrupt air travel and global trade. Some models even suggest the eruption could lower global temperatures by 3 to 5 degrees Celsius, enough to trigger famine and economic collapse on a worldwide scale. But is such a scenario likely? According to the U.S. Geological Survey, USGS, there's no evidence that an eruption is imminent. Yellowstone is being watched by an array of sensors, from GPS stations to seismic monitors to satellite imagery. Any significant changes in magma pressure, gas emissions, or tremor activity would trigger alerts. As of now, Yellowstone shows no signs of unusual behavior. However, scientists continue to study past eruptions, magma chambers, and geological history to understand how supervolcanoes operate and how we might get ahead of one. Interestingly, recent research suggests that supervolcanoes might not erupt with a slow buildup like smaller volcanoes. Instead, they may remain dormant for thousands of years and then erupt suddenly with minimal warning, a geological snap. This possibility has sparked global concern and global cooperation. International science teams are now analyzing other supervolcanoes, like Campi Flegrei near Naples, Italy. This volcanic region has shown signs of ground uplift and increasing gas emissions, prompting Italian authorities to begin public education campaigns and emergency planning drills. Similarly, Lake Toba in Indonesia, the site of the largest known eruption in the last 74,000 years, is being re-examined for signs of pressure buildup and seismic unrest. But preparing for a supervolcano eruption isn't just about local response. It's about global coordination. If one of these giants erupted, the world would need to act fast, sharing resources, managing food supply chains, coordinating climate responses, and protecting vulnerable populations. It would be a test of civilization. That's why projects like GVM, Global Volcano Model, and SABRE, Stratospheric Aerosol and Gas Experiment, are so vital. They bring together volcanologists, climatologists, and disaster experts to simulate outcomes, identify hotspots, and develop early warning protocols. Some scientists are even exploring the idea of actively cooling supervolcanoes, injecting water into magma chambers to reduce pressure. While still theoretical and highly risky, these proposals underscore just how seriously the threat is taken. Because unlike earthquakes or tsunamis, a supervolcano doesn't just strike one region, it strikes the world. At Infinity Beyond, we ask the hard questions, not to spark fear, but to spark preparedness. What would it take to survive a supervolcano? How would we adapt? And could this be the disaster that finally unites humanity in global cooperation? In Segment 9, we'll explore how volcanoes on other planets, like Mars, Venus, and even Jupiter's moon Io, offer insights into our own planet's violent history, and whether volcanic activity shapes habitability across the solar system. The story isn't over. It's only growing deeper. Throughout this series, we've explored how volcanic eruptions can reshape the land, alter the atmosphere, and change human history. But what happens when an eruption doesn't just impact a region, but the entire planet? Welcome to the terrifying world of supervolcanoes. In this segment of Infinity Beyond, we investigate what defines a supervolcano, why Yellowstone has captured global attention, and whether humanity is truly prepared for an eruption that could darken skies and disrupt life for years. First, let's define the term. A supervolcano is not just a big volcano. It's a volcanic system capable of ejecting more than 1,000 cubic kilometers of material in a single eruption. That's enough to bury entire continents under ash and alter the global climate for decades. There are only a handful of supervolcanoes on Earth. These include Yellowstone caldera, USA, Lake Toba, Indonesia, Campi Flegrei, Italy, Taupo volcanic zone, New Zealand. Each of these sites is massive in scale, often covering hundreds of square kilometers, and all of them are being closely monitored by scientists. Among them, Yellowstone is perhaps the most infamous. Located in Wyoming, Yellowstone National Park sits atop a massive volcanic system that has erupted 3 times in the last 2.1 million years. The most recent eruption occurred around 640,000 years ago, forming the Yellowstone caldera, a depression so large most visitors don't even realize they're standing inside a volcano. Since then, the system has remained active, with earthquakes, geysers, and ground uplift as constant reminders of the power beneath. But here's the question that keeps researchers awake at night. Are we overdue for another super eruption? Statistically, it's complicated. While some have claimed that Yellowstone erupts every 600,000 to 700,000 years, scientists caution against using averages to predict rare geological events. Nature doesn't follow a schedule. That said, the potential consequences of an eruption are staggering. If Yellowstone were to erupt at full force, it could eject thousands of cubic kilometers of ash into the sky, create a volcanic winter, blocking sunlight and reducing global temperatures, collapse agriculture in major food-producing regions, contaminate water sources and cause mass displacement, severely disrupt air travel and global trade. Some models even suggest the eruption could lower global temperatures by 3 to 5 degrees Celsius, enough to trigger famine and economic collapse on a worldwide scale. But is such a scenario likely? According to the U.S. Geological Survey, USGS, there's no evidence that an eruption is imminent. Yellowstone is being watched by an array of sensors, from GPS stations to seismic monitors to satellite imagery. Any significant changes in magma pressure, gas emissions, or tremor activity would trigger alerts. As of now, Yellowstone shows no signs of unusual behavior. However, scientists continue to study past eruptions, magma chambers, and geological history to understand how supervolcanoes operate and how we might get ahead of one. Interestingly, recent research suggests that supervolcanoes might not erupt with a slow buildup like smaller volcanoes. Instead, they may remain dormant for thousands of years and then erupt suddenly with minimal warning, a geological snap. This possibility has sparked global concern and global cooperation. International science teams are now analyzing other supervolcanoes, like Campi Flegrei near Naples, Italy. This volcanic region has shown signs of ground uplift and increasing gas emissions, prompting Italian authorities to begin public education campaigns and emergency planning drills. Similarly, Lake Toba in Indonesia, the site of the largest known eruption in the last 74,000 years, is being re-examined for signs of pressure buildup and seismic unrest. But preparing for a supervolcano eruption isn't just about local response. It's about global coordination. If one of these giants erupted, the world would need to act fast, sharing resources, managing food supply chains, coordinating climate responses, and protecting vulnerable populations. It would be a test of civilization. That's why projects like GVM, Global Volcano Model, and SABRE, Stratospheric Aerosol and Gas Experiment, are so vital. They bring together volcanologists, climatologists, and disaster experts to simulate outcomes, identify hotspots, and develop early warning protocols. Some scientists are even exploring the idea of actively cooling supervolcanoes, injecting water into magma chambers to reduce pressure. While still theoretical and highly risky, these proposals underscore just how seriously the threat is taken. Because unlike earthquakes or tsunamis, a supervolcano doesn't just strike one region, it strikes the world. At Infinity Beyond, we ask the hard questions, not to spark fear, but to spark preparedness. What would it take to survive a supervolcano? How would we adapt? And could this be the disaster that finally unites humanity in global cooperation? In Segment 9, we'll explore how volcanoes on other planets, like Mars, Venus, and even Jupiter's moon Io, offer insights into our own planet's violent history, and whether volcanic activity shapes habitability across the solar system. The story isn't over. It's only growing deeper. For centuries, we believed volcanoes were uniquely earthly phenomena, molten rock erupting from within a living, geologically active planet. But space exploration has rewritten that idea entirely. Volcanoes are everywhere in the solar system. From the towering mountains of Mars to the lava fountains of Jupiter's moon Io and the smoldering plains of Venus, alien eruptions are not only real, they're redefining how we think about planetary evolution, geology, and even the potential for extraterrestrial life. In this segment of Infinity Beyond, we take you on an interplanetary journey through the most powerful volcanic worlds beyond Earth. Let's begin with the giant among giants, Olympus Mons on Mars, rising 22 kilometers high, nearly 3 times the height of Mount Everest. Olympus Mons is the largest volcano in the entire solar system. Its base spans 600 kilometers across, and its gentle slopes suggest it was built by slow, massive lava flows over millions of years. But here's what's truly fascinating. Olympus Mons is so huge because Mars lacks tectonic plates. On Earth, magma rises through shifting plates, spreading eruptions across different regions. But on Mars, the crust is fixed. This allowed magma to well up in the same location again and again, forming a superstructure of unimaginable scale. Is Olympus Mons still active? Possibly. Some researchers believe there may have been eruptions as recently as 2 million years ago, very recent on a geological timescale. Next, we head to one of the most violent volcanic bodies in the entire solar system, Io, a moon of Jupiter. Io is unlike anything in the solar system. Its surface is constantly erupting with lava fountains, plumes, and sulfur geysers that reach hundreds of kilometers into space. These eruptions are caused not by internal heat from radioactive decay, like on Earth, but by tidal heating. As Io orbits Jupiter, it's pulled and stretched by the planet's immense gravity and the gravitational forces of neighboring moons. This flexing creates friction and heat inside Io's core, fueling endless volcanic activity. Some eruptions on Io are so powerful that they've been captured from Earth-based telescopes. One eruption in 2007 sent material 330 kilometers above the surface, an eruption visible across millions of kilometers of space. Io is the most volcanically active world we know of, and it offers a glimpse into what extreme geological activity looks like in environments very different from Earth. Then there's Venus, Earth's twisted twin. Shrouded in dense clouds of sulfuric acid and with surface temperatures hot enough to melt lead, Venus once appeared geologically dead. But recent radar imaging has shown possible signs of active volcanism, including hotspots, dome formations, and surface changes captured between satellite flybys. Unlike Earth, Venus doesn't have plate tectonics. Instead, it may undergo catastrophic resurfacing events, where massive amounts of lava erupt across the entire planet every few 100 million years. But smaller, ongoing eruptions may also be happening beneath the clouds, possibly releasing volcanic gases into the atmosphere. One particular volcano, Mat Mons, has been identified as a likely candidate for recent activity, and upcoming missions like Veritas and Envision will investigate further. Why does this matter? Because volcanoes play a critical role in shaping planetary environments and potentially supporting life. On icy moons like Europa, Jupiter, and Enceladus, Saturn, volcanic activity takes a very different form. Instead of molten rock, these worlds have cryovolcanoes, which erupt liquid water, ammonia, or methane. These icy eruptions may indicate subsurface oceans, heated by tidal forces and insulated by thick ice crusts. In these hidden oceans, powered by volcanic vents, scientists believe life could exist, not unlike the microbial life that thrives near hydrothermal vents at the bottom of Earth's oceans. Volcanoes, in this sense, aren't just destructive. They're potential life-givers. They provide heat, nutrients, and energy in otherwise frozen, hostile environments. They may even create atmospheres by releasing gases over millions of years, a process thought to have helped shape Earth's early climate. As we explore the solar system, we're starting to see that volcanism is a universal process, one that transcends Earth and connects us to distant worlds. Each eruption, whether it happens in Wyoming or on Jupiter's moons, tells a story about a planet's interior, its evolution, and its potential to host life. So what's next? NASA and ESA missions are set to explore these alien volcanoes up close. Europa Clipper will fly by Jupiter's moon to study its icy plumes. Mars Sample Return may help determine the age of Olympus Mons's last eruption. And Veritas will peer beneath the toxic veil of Venus to find out just how active our sister planet really is. At Infinity Beyond, we believe that understanding alien volcanoes may unlock the biggest question of all. Are we alone in the universe? Because where there is volcanic heat, there might be life. In Segment 10, we'll look toward the distant future. Could humanity one day live on or near alien volcanoes? Could we harness their energy, or will we always have to fear their power? The science fiction is becoming science fact. Stay tuned, stay curious, stay with Infinity Beyond. For centuries, volcanoes were feared as omens, God's wrath rising from the earth. But in the future, they may become something very different, a lifeline for humanity beyond Earth. In this final segment of Infinity Beyond, we imagine a bold future, where humans don't just study volcanoes from afar, but live alongside them, using their heat, minerals, and energy to build the first off-world settlements. Let's start with Mars. If humanity ever colonizes the Red Planet, volcanic regions like Olympus Mons and the Tharsis Ridge could offer unique advantages. The ground is already rich in basalt, which can be used to make building materials. And nearby subsurface heat from ancient magma chambers may still linger, offering a way to generate geothermal energy. Unlike Earth, Mars is cold and has a thin atmosphere. Keeping a colony warm will be a constant challenge. That's where lava tubes come in. Lava tubes, long underground tunnels formed by flowing lava, have been detected on Mars and the Moon. These natural caves are believed to be wide enough to hold entire cities, shielded from cosmic radiation and temperature extremes. In fact, some are over 100 meters in width and stretch for kilometers. Imagine a human base inside a Martian lava tube, protected, stable, and thermally regulated. It's not just possible, it's one of the leading ideas in NASA's colonization plans. Now let's talk about power. Volcanic regions can provide geothermal energy, tapping into underground heat to generate electricity. On Earth, countries like Iceland already use this method to power entire cities. On Mars or icy moons, geothermal systems could keep water liquid, grow crops in underground greenhouses, and sustain life. But what about the dangers? Living near a volcano, even a dormant one, is risky. While Mars may not currently be volcanically active, other worlds like Io, Venus, and Enceladus still experience eruptions. Let's take Io, for example. With hundreds of active volcanoes, Io is the most geologically violent body in the solar system. Colonizing Io itself would be nearly impossible due to constant eruptions and extreme radiation from Jupiter. But studying it from nearby orbital stations or robotic probes could yield breakthroughs in energy science and planetary dynamics. Then there's Venus, Earth's hellish twin. Its crushing atmosphere and 470-degree surface make habitation unthinkable on the ground. But floating colonies in the upper atmosphere have been proposed. In that layer, temperatures and pressures are surprisingly Earth-like. Some scientists suggest using volcanic gases or surface heat to power floating platforms suspended by giant balloons. Science fiction today, but theoretically feasible. Meanwhile, icy moons like Enceladus and Europa may offer the best of both worlds, volcanic heat and liquid water. Beneath their frozen crusts, cryovolcanism, where water and gases erupt like lava, hints at warm subsurface oceans. Colonies near these heat sources could harvest thermal energy, melt ice for water, and perhaps even discover alien microbes thriving in hidden oceans. Volcanic vents on Earth are home to life forms that don't rely on sunlight, only heat and chemistry. Could the same be true beyond our planet? This vision of the future, where fire and ice collide to create the conditions for survival, is no longer just a dream. Space agencies and private companies are investing in volcanic terrain simulation, subsurface habitat design, and lava tube exploration with robotics. One concept even involves terraforming Mars using volcanic heat, melting underground CO2 reserves to thicken the atmosphere over centuries. While massively ambitious, it shows how central planetary geology could be to our survival as a species. But why would we take such risks? Because volcanoes offer something rare in space: natural power. The ability to warm a habitat without the sun, to power systems without solar panels, to create shelter within rock instead of fragile metal domes. In short, volcanoes might be the first and best homes for humanity beyond Earth. Of course, this comes with challenges: seismic instability, gas eruptions, material corrosion, and unpredictability. But with proper planning, AI monitoring, and adaptive engineering, these risks could be mitigated. And the reward? A future where humans expand not only into orbit, but into the geological veins of other worlds. As we conclude this series on volcanoes, from Earth's cataclysmic blasts to the alien eruptions of distant moons, we're reminded of something fundamental. Where there is fire, there is life. Where there is eruption, there is change. And where there is change, there is opportunity. At Infinity Beyond, we believe volcanoes are not just symbols of destruction. They are gateways to resilience, discovery, and the future of civilization. Thank you for exploring with us. Don't forget to subscribe, share, and stay curious, because this journey is far from over.